I'm glad you've come here to meet the sound at this unique moment, wherever you may be, perhaps in a quiet bedroom lit by a solitary lamp, with only distant stars and occasional passing headlights outside the window, or perhaps you're on a long night train journey. Tonight, I'd like to gently explore a place with you. This place is both distant and right at your fingertips. It exists within all things, in the very air you breathe, deep within every cell of your body. This place is the quantum world. Perhaps you've heard its name before, finding it mysterious and filled with mathematical formulas. Perhaps you imagine it as a sacred realm accessible only to top scientists. But tonight, gently set those preconceptions aside. We'll approach it in a different way, not with complex equations or abstruse terminology, but by gently touching it with imagination and intuition. This is a story about the essence of reality, a tale of a world so minuscule it defies scale, yet governed by the grandest of laws. It explores what light is, what matter is, and the wondrous power inherent in the simple act of our observation itself. This story isn't meant to keep you awake. Quite the opposite, it might help you sleep more peacefully. For when we contemplate the universe's profound mysteries, the troubles of daily life seem especially insignificant. So relax and follow me. Let's dive together into the soft and strange quantum sea. First, let's slowly rewind our thoughts to Europe over a century ago. The physics community then exuded an air of triumphant achievement. It was a golden age brimming with certainty. Sir Isaac Newton's mechanical framework had flawlessly explained nearly all macroscopic motion, from celestial orbits to falling apples. James Clerk Maxwell unified electricity, magnetism, and light into a single phenomenon, electromagnetic waves, through his elegant equations. The laws of thermodynamics were also neatly organized. It seemed as though the universe were a precision clockwork, where every turning gear had been comprehended by humankind. Some renowned scientists even publicly declared that the grand edifice of physics was essentially complete. The work of future physicists, they claimed, would merely involve improving measurement precision by a few decimal places, or tidying up some insignificant details, like searching for the last few specks of dust hidden in the corners. Searching for the last few specks of dust hidden in the corners. Everyone believed the laws of the universe were already fully grasped. What remained were merely trivial tasks of patching and repair. Yet they did not realize that beneath the foundations of this cherished edifice of classical physics, a few minute cracks were silently appearing, and the most inconspicuous of these cracks originated precisely from a seemingly simplest question. When you heat an object, why does it emit light of a specific color? This question, seemingly the domain of craftsmen and experience, was about to become the starting point for revolutionizing the entire world of physics. Now let us focus our attention on that seemingly insignificant speck of dust. It has a rather technical-sounding name, blackbody radiation. Please don't be intimidated by the name. The phenomenon it describes is actually quite intuitive. Imagine warming yourself by a fireplace, or watching an electric stove coil slowly glow red. When metal is heated, it first emits a deep crimson light. As the temperature rises, the color shifts to bright orange and eventually yellow-white. This phenomenon of light emission due to heating is blackbody radiation. In the laboratory, scientists use an ideal blackbody, an object that perfectly absorbs and emits light of all wavelengths. To study this phenomenon precisely, they measured the distribution of energy emitted by the blackbody at different temperatures across various colors, i.e., wavelengths. This should have been a problem perfectly explainable by classical physics. However, when scientists applied the then accepted laws and formulas, To this case, the mathematics yielded an utterly absurd conclusion. The formula predicted that as the blackbody's temperature increased, its emitted energy would increasingly concentrate in the high-frequency ultraviolet region until it released infinite energy in the ultraviolet spectrum. This result was clearly absurd. It implied that any heated metal could instantly become a destructive ultraviolet bomb. This starkly contradicted everyday experience. You've never seen a red-hot iron bar emit lethal ultraviolet light illuminating a room. This colossal contradiction between theory and reality is dramatically dubbed the ultraviolet catastrophe. Like a specter, it hovers over classical physics. No matter how scientists tweak and patch the old equations, they cannot reconcile mathematical calculations with experimental curves. An unbridgeable chasm has emerged between prediction and reality. This suggests that certain foundational laws we hold as absolute may not hold true in the microscopic realm. The smooth, continuous worldview of classical physics crashed into an invisible wall here. Through this simple enigma of heat and light, the universe issued its first low, clear warning to humanity. Amidst this cloud of theoretical physics, a calm, meticulous German physicist stepped onto the stage. His name was Max Planck. Planck himself was a staunch believer in classical physics. He did not seek to overturn anything. He was simply a pragmatic scientist. Faced with the thorny problem of blackbody radiation, he resolved to find a solution that would work mathematically, no matter how strange it might appear. After arduous attempts, in the year 1900, Planck made a bold, almost desperate hypothesis. He proposed that energy might not be released as smoothly and continuously as we imagined. Instead, energy could only be emitted in indivisible, smallest units. Just as you cannot pay with half a coin, the universe, when releasing energy, also has a smallest coin unit. He called these smallest units of energy quanta. This term, derived from Latin, means how much. To quantify these energy packets, he even introduced a new fundamental constant, an exquisitely small yet critically important number, later named the Planck constant in his honor. When he substituted this seemingly heretical idea into his equations, a miracle occurred. The troubling prediction of infinite energy vanished. The curve derived from mathematical calculations, and the data obtained from experimental observations overlapped perfectly. The ultraviolet catastrophe was resolved. Yet Planck himself felt profound unease about this outcome. He did not believe it represented the true nature of physics. He preferred to see it as a mathematical trick, a clever ploy adopted out of necessity to make the math work. He himself described his discovery as an act of desperation. He sincerely hoped that future physicists would uncover an explanation more aligned with classical intuition, and thus abandon this peculiar quantum concept. He could never have foreseen that the faint spark he ignited would eventually blaze into a raging inferno engulfing the entire physics community. The tiny constant he introduced, and his mathematical trick, deemed a temporary expedient, would utterly dismantle the certain and continuous classical world, and lay the first cornerstone for an entirely new, more wondrous vision of reality. It all began with a seemingly unremarkable scientific paper, published in 1900. No fanfare, no proclamations, only a tiny constant, and a revolutionary way of thinking about energy. From that moment on, physics ceased to be a science nearing its end. At the very moment we parted ways, though cracks had appeared in the edifice of classical physics, most physicists still firmly believed The question of light's nature had been definitively resolved. It was undoubtedly a wave. This was the solemn verdict James Clerk Maxwell had inscribed for posterity. With his elegant set of equations, light could diffract like water waves, bending around the edges of obstacles. It could also produce distinct interference fringes. When two beams met, peak to peak, they combined into bright bands. Peak to trough, they canceled into dark bands. All these were the unique fingerprint of a wave, irrefutable proof of its identity. Yet the path of scientific exploration is always full of surprises. A seemingly ordinary experiment, a simple dialogue between light and metal, casts a pebble into the tranquil lake, stirring ripples that spread outward in concentric circles. This phenomenon is the photoelectric effect. Its experimental setup is straightforward. Imagine a dark room containing a pure metal plate. When a beam of light strikes this metal plate, scientists were astonished to discover tiny electrons are knocked off the metal surface into the surrounding space. This itself seems not difficult to comprehend. Light as a wave carries energy. When this wave of energy washes over the metal surface, it naturally transfers some of its energy to the electrons bound within the metal. Much like how ocean waves washing over a beach can push grains of sand far away. Based on the classical wave theory held as gospel at the time, several clear predictions could be made. The energy of light is directly proportional to its intensity, its brightness. Brighter light implies more powerful energy waves. Therefore, first, increasing light brightness should cause ejected electrons to carry higher kinetic energy, flying faster and farther. Second, as long as light is sufficiently bright, regardless of its color, it should theoretically be able to eject electrons. Weaker light might simply require more time to accumulate energy. However, when scientists entered the laboratory, for precise measurements, they obtained results that were utterly astonishing. These findings contradicted the predictions of wave theory. At every turn, they discovered that while increasing the intensity of the incident light did indeed cause more electrons to escape from the metal, the velocity at which these electrons flew out and their kinetic energy remained completely unchanged. It was as if you struck a water surface with both a downpour and a light drizzle. Heavy rain creates more splashes, but each droplet reaches the same height. What puzzled scientists even more was that the key factor determining electron ejection was not light intensity but light color or frequency. When using high-frequency light like blue or ultraviolet, even faint light akin to fireflies, the ejected electrons possess remarkably high energy, as if they were tiny bullets. Yet when using lower frequency light, such as red light, no matter how intensely you amplify it, to the blinding brightness of a red-hot iron bar, the metal surface stubbornly remains silent. Not a single electron escapes. Here lies a clear and decisive frequency threshold, an invisible barrier. Wave theory utterly fails to explain this sharp threshold. Cannot comprehend why electron escape. Depends solely on whether the key of light's color fits. While the intensity of light, the force of knocking, remains irrelevant. It's like a gentle yet high-pitched song, shattering delicate crystal glasses, while a deafening, deep, resonant drumbeat leaves the glass untouched. This silent, stubborn contradiction between light and metal becomes a persistent specter, haunting the realm of classical physics. It lies quietly in the laboratory notebooks, awaiting a wise mind capable of deciphering its code, to examine this seemingly simple world with entirely new eyes. Resolving this contradiction would not merely explain an experimental phenomenon, but would fundamentally reshape our understanding of light and reality itself. Now, Immerse yourself in the subtle tension this puzzle creates, and feel the helplessness of old theories confronting new facts. This very confusion is the hidden engine driving science forward. Carrying this unresolved question, we may let our thoughts rest, to make space for the breakthrough to come. When classical wave theory faltered before the photoelectric effect experiment, a young physicist proposed a revolutionary solution. In 1905, Albert Einstein systematically presented his light quantum hypothesis. In the paper Heuristic Viewpoint concerning the production and conversion of light, now regarded as a milestone in quantum theory's development, Einstein's insights stemmed from his profound analysis of thermal radiation and the photoelectric effect. He keenly observed that Planck's solution to the blackbody radiation problem implied an underlying physical reality not yet fully grasped. In Planck's theory, while energy was quantized during radiation and absorption, the electromagnetic field itself was still treated as a continuous wave. Einstein ventured further than his predecessors. He boldly proposed that light's energy distribution in space is also discontinuous. According to Einstein's hypothesis, light consists of discrete energy quanta that exist and move locally within space. Each light quantum carries a specific amount of energy, proportional to the light's frequency, by the relationship E equals h nu, where E represents energy, nu is the light's frequency, h is the fundamental action quantum introduced by Planck. This is the famous Einstein equation for the photoelectric effect. Within this entirely new theoretical framework, each light quantum, later termed a photon, constitutes a complete energy packet. When light interacts with matter, energy is exchanged in units of entire light quanta. A photon either transfers its entire energy to an electron, or transfers none at all. Partial energy transfer does not occur. This assumption perfectly explains all key features of the photoelectric effect. Regarding the frequency threshold phenomenon, Einstein's theory provides a clear physical explanation. Electrons in metals must overcome a certain work function to escape the surface. Only when the energy of a single photon h nu exceeds this work function can an electron potentially be ejected. If the photon's energy is less than the work function, no matter how many photons strike the metal surface, no single photon possesses sufficient energy to eject an electron, and thus no photoelectron is produced. Regarding the puzzle of photoelectron kinetic energy being independent of light intensity, Einstein's theory also provides a compelling explanation. Light intensity only determines the number of incident photons per unit time, and thus affects the quantity of emitted photoelectrons. However, the kinetic energy of each ejected electron depends solely on the incident photon's energy minus the work function, and is independent of light intensity. This explains why increasing light intensity only amplifies the photoelectric current, without altering the maximum initial kinetic energy of photoelectrons. Einstein's photoelectric hypothesis elevated Planck's quantum concept to a new level. For Planck, quantization remained a formal hypothesis, primarily used to explain energy exchange processes. Einstein, however, asserted that light's quantum nature is an inherent fundamental property of light itself. This was not merely an explanation of experimental phenomena, but also a redefinition of light's very nature. This revolutionary theory faced skepticism from many physicists at the time. Numerous renowned scholars, including Planck himself, struggled to accept the notion of light possessing particle-like properties. After all, light's wave nature was supported by substantial experimental evidence. Phenomena like interference, diffraction, and polarization seemed fundamentally incompatible with the particle theory. Yet Einstein maintained that both the wave and particle nature of light represent different aspects of its essence. Under varying experimental conditions, light exhibits distinct characteristics. It displays wave-like behavior during propagation, while interacting with matter. It manifests particle-like properties. This seemingly contradictory dual nature reflects the profound harmony and unity inherent in nature. With advances in experimental techniques, particularly through a series of meticulously designed experiments by American physicist Millikan, Einstein's photoelectric effect equation was ultimately validated. The photon hypothesis, initially a radical and heavily contested viewpoint, gradually gained acceptance within the physics community, becoming a cornerstone of modern physics. Einstein received the 1921 Nobel Prize in Physics, not for his more famous theory of relativity, but for his explanation of the photoelectric effect. This fact fully demonstrates the pivotal role of the photon hypothesis in the history of physics. It not only resolved a specific experimental challenge, but more significantly, paved a novel intellectual path for the entire development of quantum mechanics. The introduction of the photon concept marked physics' entry into a new era. It shattered classical physics notions of continuity and absolute certainty, introducing a radically new, discontinuous, probabilistic view of nature. This paradigm shift proved more profound than any specific technological application. It fundamentally transformed humanity's understanding of matter and radiation. From the perspective of modern physics, the photon has become an integral member of the standard model of elementary particles. It serves not only as the medium for electromagnetic interactions, but also as a key to understanding the early evolution of the universe and various high-energy astrophysical processes. The photon hypothesis proposed by Einstein a century ago continues to profoundly influence the development of physics. When we reflect on this chapter of scientific history, we cannot help but be awed by Einstein's extraordinary insight and theoretical courage. While others followed established paths, he dared to challenge authority and break free from traditional constraints, proposing a theory that seemed almost absurd at the time, yet ultimately proved to be revolutionary truth. This spirit of scientific innovation deserves perpetual study and reverence by future generations. The establishment of the photon hypothesis propelled physics to unprecedented philosophical depth. We were compelled to confront a fundamental question. What exactly is light? Is it a particle or a wave? The answer to this question ultimately pointed toward a new understanding transcending classical concepts: the wave-particle duality. The wave-particle duality is not a compromise formulation, but an accurate description of light's essence. Light possesses both wave-like and particle-like properties. These two natures are not mutually exclusive, but complementary. Together, they form the complete picture of light. Like two sides of a coin, we cannot see both sides simultaneously, yet both sides are the coin's true existence. From an experimental perspective, when light passes through a double-slit apparatus, it exhibits distinct interference fringes, clear evidence of its wave nature. When light interacts with metal to produce the photoelectric effect, it displays particle-like characteristics, transferring energy in discrete packets. The key lies in this dual nature of light, revealing different facets under varying experimental conditions. Niels Bohr's principle of complementarity provides a philosophical framework for understanding this phenomenon. He posited that wave-like and particle-like properties are two complementary descriptions of light. Each description is partially correct, but incomplete on its own. Only by integrating both descriptions can we achieve a comprehensive understanding of light's essence. This way of thinking radically transcends classical physics' binary, either-or dualism. The profound implications of wave-particle duality extend far beyond the realm of optics itself. It reveals fundamental laws governing the microscopic world. Inspired by this concept, de Broglie proposed that all matter exhibits wave-particle duality, including electrons, protons, and even macroscopic objects. This bold hypothesis was later confirmed by electron diffraction experiments, laying a solid foundation for the development of quantum mechanics. From an epistemological perspective, wave-particle duality teaches us that the essence of nature may forever remain, beyond complete description by any single conceptual framework. The language and concepts we employ are built upon macroscopic experience. When delving into the microscopic realm, we must prepare to embrace new modes of thinking that transcend everyday experience. This duality is not a flaw in knowledge, but an intrinsic characteristic of nature. It demands we maintain open-mindedness to accept seemingly contradictory phenomena as potentially coexisting. In modern quantum field theory, the wave-particle duality of light achieves deeper unification, where photons are regarded as quantum excitations of the electromagnetic field, simultaneously preserving the field's continuous characteristics, while exhibiting the discrete nature of particles. The discovery of wave-particle duality not only altered the trajectory of physics, but profoundly reshaped human modes of thought. Teaches us that reality may be richer and more complex than we imagine. Any single perspective may fail to capture its full truth. The double-slit experiment's apparatus is surprisingly simple, requiring only 3 core components: a reliable light source, an opaque screen with 2 parallel slits, and an image-receiving screen. This minimalist design holds the power to reveal profound cosmic mysteries. The choice of light source has evolved over time. Early experiments likely used simple incandescent bulbs or arc lamps. Modern precision experiments employ lasers as light sources, due to their ability to produce beams with pure frequency and excellent directionality. Regardless of the source, its core function is to provide a stable stream of photons. The design of the slit plate is critical. Typically made of metal or specialized composite materials, its 2 slits must be sufficiently narrow, with widths comparable to the wavelength of light, usually in the hundreds of nanometers. The spacing between the slits requires precise control. Too close or too far apart will compromise the clarity of the interference pattern. This seemingly ordinary plate serves as the dividing line between reality and illusion. The receiving screen is key to recording the phenomenon. In Thomas Young's era, a simple white screen was used. Observations were recorded by the naked eye. Modern experiments employ high-sensitivity photodetector arrays, or fluorescent screens paired with high-speed camera systems, capable of capturing the arrival position of individual photons. Environmental control in the experiment is equally critical. To obtain a clear interference pattern, the entire optical system must be mounted on an anti-vibration platform to prevent minute vibrations from interfering with the results. Airflow and temperature fluctuations must also be tightly controlled. These details ensure the reliability of observational results. The experimental procedure is remarkably straightforward. Align the light source with the double-slit aperture. Adjust the distance and angle between the 3 components until a stable pattern emerges on the screen. This simple process reveals the fundamental distinction between the classical and quantum worlds. The experiment's appeal lies in the fact that anyone can replicate it in a suitably equipped laboratory. The required equipment is commonplace in modern research institutions. Yet this seemingly ordinary apparatus has become one of quantum mechanics' most famous thought experiments, and a key gateway to understanding quantum phenomena. When everything is ready, and the light source is switched on, we begin a dialogue with the essence of nature. Through this rudimentary device, the universe whispers to us, revealing profound truths about the nature of reality. Within the framework of classical physics, the behavior of waves and particles has distinct and clearly defined expectations. These expectations are built upon centuries of observation and theory, forming the intuitive foundation of our worldview. When water waves pass through a double slit, typical wave phenomena occur. Circular wavefronts emitted from the source reach the double slit barrier. Each slit becomes a new secondary source, emitting coherent subwaves. These subwaves propagate behind the barrier and interfere with each other. Wave interference follows precise mathematical laws. At certain points in space, two subwaves meet peak to peak. Their amplitudes add constructively. These regions exhibit amplified wave amplitudes. At other points, peaks meet troughs. Amplitudes cancel destructively. These regions show minimal or zero wave amplitude. For light waves, constructive interference corresponds to bright regions, while destructive interference corresponds to dark regions. Consequently, on the receiving screen, alternating parallel bands of light and dark are observed. This constitutes the interference pattern of light. The spacing of these bands is jointly determined by the wavelength of light and the geometric parameters of the double slit. In stark contrast, the expected behavior of classical particles would be as follows. If small particles, such as fine sand or metal spheres, were fired at the double slit, behind the screen, two bright regions, corresponding to the positions of the two slits. According to classical mechanics, the particle's trajectory is deterministic. Each particle possesses a definite position and momentum, which slit it passes through, and where it ultimately lands on the screen can theoretically be predicted. No interference phenomenon occurs. This difference in wave-particle behavior is absolute in classical physics. A substance either behaves as a wave or as a particle. It cannot possess both properties simultaneously. This dichotomy in the macroscopic world has been confirmed by countless experiments. When predicting the outcome of the double-slit experiment, from a classical physics perspective, the expectation is clear and unambiguous. If light is a wave, we should observe interference fringes. If light is a particle, we should see two bright spots. This explicit expectation makes the actual experimental results appeared all the more perplexing and astonishing, because they neither fully matched the wave prediction nor fully matched the particle prediction, but instead exhibited a new behavior beyond classical categories. This certainty of prediction in the classical world provides us with a crucial frame of reference. Only by contrasting it with actual observational results can we gain a deeper understanding of the revolutionary significance of quantum phenomena. This cognitive conflict is precisely the driving force behind the development of quantum mechanics. When experimental techniques advanced to the point of controlling single photon emission, the double-slit experiment yielded its most perplexing results. Scientists engineered an extremely faint light source, ensuring that at any given moment, only one photon at most would travel toward the double-slit apparatus. Each photon was sufficiently separated from preceding and following photons to eliminate the possibility of photon interactions. Under these single-photon conditions, the classical particle model predicted that each photon would pass through only one slit, resulting in two distinct bright spots on the screen. Yet the actual experimental outcome completely overturned this expectation. At the start of the experiment, the screen initially displayed seemingly randomly distributed light spots, each representing the arrival position of a single photon. Over time, the accumulated dots gradually formed alternating bright and dark interference fringes. This phenomenon fundamentally challenges the intuition of classical physics. This result raises a profound question. How can a single photon interfere with itself? If each photon truly passes through only one slit, where does the interference pattern come from? The only reasonable explanation is that each photon simultaneously passes through both slits and interferes with itself. Quantum mechanics explains this through the concept of the wave function. Before measurement, a photon has no definite location, but exists as a probability wave. This probability wave passes through both slits simultaneously, just like a real wave. The wave fronts at both slits interfere with each other, forming complex interference patterns. The photon's wave function contains complete information about its possible paths. As the wave function passes through the double slit, it explores all possible routes, including paths where it passes through both slits simultaneously. The wave function components of these possible paths interfere with each other, determining the probability distribution of where the photon is ultimately detected. At the detection screen, the wave function collapses, and the photon randomly chooses to appear at one of the permitted positions within the interference pattern. The landing point of a single photon appears random, but the statistical distribution of numerous photons precisely reproduces the interference fringes predicted by wave theory. This phenomenon holds true not only for photons. Subsequent experiments replicated similar setups using electrons, neutrons, and even molecules, all observing identical interference behavior. In 1999, a research team at the University of Vienna successfully observed molecular interference using fullerene molecules, extending quantum behavior to larger mass scales. The significance of single-photon interference experiments lies in their exclusion of any interpretation based on classical particle interactions, demonstrating that quantum behavior is an intrinsic property of individual particles, rather than a statistical effect of particle ensembles. This experimental result continues to challenge our intuition, yet it perfectly aligns with the mathematical description of quantum mechanics. The Schrödinger equation precisely predicts the shape of the interference pattern, validating the self-consistency and predictive power of quantum theory. When scientists attempt to determine which specific slit a photon passes through, an even more astonishing phenomenon occurs. Any experimental setup designed to measure the photon's path causes the interference pattern to vanish, replaced by two simple bright spots. This phenomenon is termed quantum decoherence, revealing the unique status of measurement in the quantum realm. In the double-slit experiment, scientists install detectors at the slits to record the path information of each photon. When the path detector is activated, regardless of the detector's precision, or whether data is actually recorded, the interference fringes vanish instantly. Only two bright spots appear on the screen, corresponding to the expected behavior of classical particles. Quantum mechanics explains this by stating that the interaction between the measuring instrument and the quantum system causes the wave function to collapse. When the detector measures a photon's path, it forces the photon to choose a definite path, thereby destroying the original quantum superposition state. According to the Copenhagen interpretation, before measurement, the photon exists in a superposition state of passing through both the left and right slits. The act of measurement forces the system to select a definite state. This selection of state is probabilistic, following the probability distribution given by the wave function. From the perspective of quantum information, the acquisition of path information destroys the quantum coherence required for interference. Interference arises from phase relationships between different paths. Yet the measurement process inevitably introduces random phases. Undermining this delicate quantum correlation, experiments demonstrate even the mildest measurements destroy interference. The critical factor is whether path information can potentially be obtained, not whether it is actually acquired. If an experimental setup could theoretically distinguish paths, interference vanishes. A particularly ingenious experimental setup is the quantum erasure device, which allows scientists to erase path information after photons pass through a slit. When path information is erased, interference fringes miraculously reappear. This experiment demonstrates the critical factor is traceable path information, rather than the measurement process itself. The observer effect sparks profound reflection on the nature of measurement. What constitutes measurement? Is it human consciousness or physical interaction? The modern view holds that any irreversible interaction with the macroscopic environment is sufficient to cause decoherence. In decoherence theory, the measuring apparatus is regarded as part of the environment. When a quantum system becomes entangled with the environment, its quantum properties rapidly vanish, manifesting as classical behavior. This process explains why macroscopic objects rarely exhibit quantum effects. The observer effect in the double-slit experiment holds not only fundamental theoretical significance, but also practical applications in quantum information technology. In quantum computing, maintaining the coherence of qubits and avoiding premature decoherence represent critical technical challenges. This phenomenon reminds us that in the quantum realm, the observer is no longer an independent bystander, but an active participant in the experimental system. What we choose to measure determines what reality we perceive. Quantum mechanics does not describe an objective world independent of observation, but rather the statistical patterns of outcomes obtainable when observers interact with systems. This realization fundamentally transformed our understanding of science and the nature of reality. The success of classical physics in the macroscopic world is undeniable. Newtonian mechanics precisely predicts the trajectories of celestial bodies. Maxwell's equations unified the phenomena of electricity and magnetism. The laws of thermodynamics explained the fundamental principles of energy transformation. However, when scientific exploration entered the microscopic realm, this well-established theoretical framework began to reveal fundamental limitations. From the late 19th to the early 20th century, experimental physicists successively discovered a series of phenomena that could not be explained by classical theory. The spectral distribution of blackbody radiation deviated significantly from theoretical predictions. The wave theory of light completely failed in the photoelectric effect. Atomic spectra exhibited discontinuous line structures. These experimental facts collectively pointed to one conclusion: microscopic particles obey different laws of motion than macroscopic objects. The fundamental assumptions of classical physics no longer hold at the atomic scale. Its core issues manifest primarily in three aspects. First, classical theory was founded on the concept of continuity, assuming physical quantities like energy, momentum, and angular momentum could vary continuously. Yet, experimental evidence showed these quantities were quantized in the microscopic realm and could only take specific discrete values. Second, classical mechanics adhered to a strict principle of determinism, claiming that knowing a system's initial state would allow precise prediction of its future trajectory. However, in the microscopic world, Heisenberg's uncertainty principle states that we cannot simultaneously measure a particle's position and momentum with absolute precision. This uncertainty does not stem from limitations in measurement technology, but represents an inherent characteristic of nature. Third, classical physics maintains a clear distinction between particles and waves. Particles possess definite positions and momenta, while waves exhibit interference and diffraction phenomena. However, quantum phenomena reveal that microscopic particles simultaneously display both wave-like and particle-like properties. This wave-particle duality cannot be understood within the classical framework. Schrödinger recognized this fundamental problem in 1926. He understood the need to establish an entirely new mathematical framework to describe the motion laws of microscopic particles. This new theory must explain quantization phenomena, accommodate inherent uncertainty, and unify the contradictions of wave-particle duality. The fundamental reason classical physics fails at the microscopic scale lies in its attempt to directly extrapolate macroscopic experience to the microcosm. In reality, microscopic particles follow entirely different laws of motion. The establishment of quantum mechanics was not a patchwork repair of classical physics, but a complete conceptual revolution. New physical laws necessitated probabilistic descriptions, abandoning the precise concept of trajectories, and accepting the wave function as the fundamental means to describe a system's state. This shift, both philosophically and mathematically, marked physics' entry into an entirely new era. The wave function stands as the core concept of quantum mechanics. It is a complex valued function, containing all observable physical information of a quantum system. In positional representation, the wave function is typically denoted as psi x t, where x represents position and t represents time. The function's values themselves hold no direct physical meaning, but the square of its absolute value, psi x t superscript 2, represents the probability density of finding the particle at position x at time t. The mathematical properties of the wave function determine the behavior of quantum systems. It must be single-valued, continuous, and square integrable. These mathematical requirements ensure the consistency of the probabilistic interpretation. The values of the wave function at various points in space do not represent some physical quantity of the particle at that point, but rather describe the likelihood of the particle appearing there. This concept differs entirely from classical particles. Before measurement, a quantum particle has no definite location. Instead, it is diffused throughout space in a certain manner. The wave function describes the mathematical form of this diffused state. It can be visualized as a probability cloud. Where the cloud's density is higher, the probability of the particle appearing is greater. Where the cloud's density is lower, the probability of the particle appearing is smaller. The evolution of the wave function follows the Schrödinger equation. This is a partial differential equation that determines how the wave function changes over time. Unlike Newton's equations, the Schrödinger equation describes the evolution of probability amplitudes, rather than the motion of a definite trajectory. This evolution is deterministic. Given the wave function at an initial time, the wave function at any future time can be uniquely determined. The principle of quantum superposition is a fundamental property of the wave function. If psi and psi2 represent possible states of a system, then their linear combination a psi plus b psi2 is also a possible state of the system. This principle led to the famous Schrödinger's cat thought experiment and forms the theoretical foundation of quantum computing. The wave function contains all information about the system. Through appropriate mathematical operations, one can extract from the wave function the probability distributions of physical quantities such as particle momentum, energy, and angular momentum. This extraction process corresponds to the operator theory in quantum mechanics. Each observable physical quantity corresponds to a Hermitian operator. During measurement, the wave function undergoes collapse. When measuring a specific physical quantity of the system, the wave function randomly collapses into an eigenstate of that quantity. This process is termed wave function collapse, or the measurement postulate. It remains one of the most controversial concepts in quantum mechanics. The global properties of the wave function are also crucial. The wave functions of identical particles exhibit specific symmetries. Bose particles possess symmetric wave functions, while fermions have antisymmetric wave functions. This symmetry requirement directly leads to important quantum phenomena such as Bose-Einstein condensation and the Pauli exclusion principle. From a more modern perspective, the wave function can be regarded as a complete description of the state of a quantum system. In quantum information theory, the wave function carries the information of qubits. Its rich mathematical structure grants quantum computing potential advantages over classical computation. Understanding the concept of the wave function is a crucial step into the quantum world. It challenges our intuitions about the nature of reality, yet provides the most successful framework for describing the behavior of microscopic particles. Although debates about the nature of the wave function persist, its predictive power has been verified in countless experiments. As the core dynamical equation of quantum mechanics, the Schrödinger equation describes the precise rules governing the evolution of the wave function over time. This partial differential equation is both elegant and profound in form. Unlike Newton's equations in classical mechanics, the Schrödinger equation does not describe changes in particle trajectories, but rather the evolution of probability amplitudes. This evolution is entirely deterministic. Given the wave function at an initial time, we can precisely predict the wave function at any future time. By solving the Schrödinger equation, the wave function evolves continuously and smoothly over time, much like ripples spreading across a water surface. This continuity ensures stable changes in the probability distribution. In the absence of measurement, the quantum system evolves predictably and continuously according to the Schrödinger equation. A predictable, continuous evolution. Solutions to the Schrödinger equation exhibit rich physical behavior. For stationary problems, the wave function can be decomposed into the product of a spatial part and a temporal part. The spatial part is determined by the stationary Schrödinger equation, while the temporal part manifests as simple phase oscillations. This method of separating variables forms the basis for solving quantum system energy levels. During temporal evolution, phase changes in the wave function are crucial, although the phase itself does not directly affect probability distributions. Phase differences between different paths determine the emergence of interference effects. This is the key distinction between quantum and classical phenomena. The Schrödinger equation satisfies the law of probability conservation. Throughout the entire evolution process, the total probability of a particle appearing in all space remains constant at 1. This vital property is guaranteed by the equation's Hermitian nature, embodying the self-consistency of quantum mechanics. Notably, during the measurement process, the evolution of the wave function temporarily deviates from the Schrödinger equation, undergoing what is termed wave function collapse. This discontinuous transformation stands in stark contrast to the smooth evolution described by the equation, and forms the core of the quantum measurement problem. One of quantum mechanics' most brilliant achievements is its perfect explanation of atomic stability and structure. By solving the Schrödinger equation for the hydrogen atom, we obtain the electron's wave function. These specific solutions correspond to different energy levels and orbitals. Thus, the concept of atomic orbitals was born. S orbitals exhibit spherical symmetry. P orbitals have dumbbell-shaped structures. D orbitals exhibit more complex geometries. These orbitals represent the spatial distribution of the electron wave function, describing the probability density of electron occurrence. Quantum numbers naturally emerge from these solutions. The principal quantum number n determines the energy level magnitude. The angular quantum number L dictates the orbital shape. The magnetic quantum number m defines the spatial orientation. The spin quantum number ms characterizes the intrinsic angular momentum. This quantum number system provides a perfect explanation for the periodic law of elements. In chemical bonding theory, quantum mechanics provides a solid theoretical foundation. Both valence bond theory and molecular orbital theory are built upon the principles of quantum mechanics. The mechanisms and rates of chemical reactions can now be understood from the perspective of electron wave functions. The entire theoretical foundation of semiconductor technology is entirely based on quantum mechanics. Band theory explains the differences between conductors, insulators, and semiconductors, the design of doping processes, and the operating principle of p-n junctions. All rely on a profound understanding of electron wave functions. Laser technology is a direct application of quantum mechanics. The concept of stimulated emission originates from Einstein's research on light-matter interactions. The realization of population inversion depends on precise control of the quantum properties of atomic energy levels. The coherence of lasers is fundamentally an expression of quantum mechanical phase consistency. Nuclear magnetic resonance imaging technology is based on the quantum behavior of atomic nuclei in magnetic fields. Different nuclear spin states exhibit minute energy level splittings. By detecting transitions between these energy levels, we can obtain detailed information about the internal structure of matter. This technology is indispensable in medical diagnostics. The advent of the scanning tunneling microscope enabled humanity to see atoms for the first time. Its operating principle is the quantum tunneling effect. By measuring the tunneling current between the tip and the sample, enables atomic resolution observation of surface structures. Quantum mechanics also explains superconductivity. Cooper pair formation, the success of BCS theory, is built upon quantum mechanics. Research into high-temperature superconductivity continues to advance quantum theory. From smartphones to GPS systems, from solar cells to medical imaging equipment, nearly every corner of modern technology rests upon the bedrock of quantum mechanics. This theory describing the behavior of the microscopic world has profoundly transformed our macroscopic lives. The success of quantum mechanics lies not only in its predictive power, but also in its provision of a new paradigm for understanding nature. Within this paradigm, we have learned to reinterpret our world through the lens of probability and the language of wave functions. In our familiar everyday world, determining an object's position and momentum is taken for granted. Through GPS, we can precisely pinpoint a car's location. Via speed sensors, we can simultaneously gauge its velocity. Both measurements can achieve satisfactory accuracy at the same time. But in the microscopic quantum realm, such certainty is replaced by a profound natural law. Heisenberg's uncertainty principle reveals a remarkable fact. We can never simultaneously know with precision both the position and momentum of a microscopic particle. There exists an inherent constraint on the measurement accuracy of these two fundamental physical quantities. When we seek to precisely determine a particle's position, we must sacrifice our understanding of its momentum. Conversely, If we wish to accurately know a particle's momentum, we must accept uncertainty in our knowledge of its position. This relationship does not stem from imperfect experimental techniques, but from a fundamental law inherent in nature. It's like trying to capture both sides of light and shadow simultaneously. When we focus on one aspect, the other becomes elusive. Imagine observing an electron with light. To precisely determine its position, we need light with a very short wavelength. Such light provides high spatial resolution, but short wavelengths mean high energy. When these photons collide with the electron, they severely disturb its motion, blurring our perception of its momentum. If we switch to longer wavelengths, the disturbance to the electron's momentum does decrease. But the cost of longer wavelengths is our inability to precisely determine the electron's exact location. This trade-off is not a technical flaw, but a fundamental law governing the quantum world. This uncertainty relationship exists not only between position and momentum, but also between other pairs of physical quantities. For instance, a similar constraint exists between energy and time. At extremely short timescales, measuring energy reveals an inherent uncertainty. This principle profoundly reshapes our understanding of the material world. At the quantum scale, particles no longer possess precise trajectories in the classical sense. We can only describe their whereabouts through probabilistic clouds. This intrinsic fuzziness is one of the most fundamental characteristics of the quantum realm. The Heisenberg uncertainty principle is often mistakenly interpreted as merely an inevitable consequence of measurement interference. In reality, this understanding is not entirely accurate. The principle reveals an intrinsic property of quantum systems themselves, rather than a limitation of measurement techniques. Even if we could design a perfect measuring device that completely avoids any interference with the system, the uncertainty principle would still hold strictly. This is because it is rooted in the fundamental nature of the quantum world, a basic manifestation of natural laws. From a fundamental physics perspective, this uncertainty originates from the wave-particle duality of matter, where every microscopic particle simultaneously exhibits both particle and wave properties. The fundamental nature of waves dictates that they cannot possess both a definite position and wavelength simultaneously. A wave packet highly localized in space necessarily contains components of various wavelengths, correspondingly exhibiting significant uncertainty in its momentum. Conversely, if a wave possesses a well-defined wavelength, then it must be extensively spread out in space, rendering its position indistinct. This fundamental characteristic of waves manifests in the quantum realm as the uncertainty relation between position and momentum. Within the mathematical framework of quantum mechanics, this uncertainty stems from the non-commutativity of fundamental operators, the operators representing the physical quantities of position and momentum mathematically fail to satisfy the commutative law. This mathematical property directly gives rise to the physical uncertainty relation. Experimental observations have fully confirmed this. No matter how advanced measurement techniques become, no matter how sophisticated experimental apparatus grows, we can never overcome this fundamental constraint. This is not because our instruments lack precision, but because nature itself operates in this manner. In the macroscopic world, this uncertainty is scarcely perceptible due to its minuscule impact. Yet, at the atomic and subatomic scales, it exerts a decisive influence, governing all behaviors of microscopic particles. This inherent fuzziness is not a flaw in our knowledge, but an essential characteristic of nature. Tells us that in the microscopic realm, precision and certainty must yield to descriptions based on probability and statistics. Heisenberg's uncertainty principle is not merely an abstract theoretical concept. It has profound and concrete implications for understanding how the material world operates. From the stability of atoms to the luminosity of stars, from the nature of vacuum to the advancement of modern technology, all rely on the influence of this fundamental principle. Consider the question of why atoms can remain stable. According to classical electromagnetic theory, electrons orbiting the nucleus would continuously radiate energy, eventually spiraling into the nucleus in an extremely short time. Yet experiments reveal atoms are remarkably stable systems, with electrons never crashing into the nucleus. The uncertainty principle offers a perfect explanation. If an electron is confined to an extremely small space near the nucleus, according to the uncertainty principle, its momentum becomes highly indeterminate. This implies the electron must possess significant kinetic energy. This pressure generated by quantum effects effectively counteracts the electrostatic attraction of the nucleus, maintaining the stability of atomic structure. The size of an atom precisely reflects the delicate balance between electromagnetic attraction and quantum repulsion. We can estimate the typical size of an atom based on the uncertainty principle, and the result matches experimental measurements remarkably well. This marks the first major triumph of the uncertainty principle. In stellar physics, this principle also plays a crucial role. It enables atomic nuclei to overcome their mutual electrostatic repulsion and undergo fusion reactions through quantum tunneling. The immense energy of the Sun and other stars originates precisely from this mechanism. Without the uncertainty principle, no stars would shine in the universe, and life itself could not have emerged. At absolute zero, the uncertainty principle ensures particles never come to complete rest, instead maintaining so-called zero-point motion. These quantum fluctuations are the origin of zero-point energy. Even in the lowest energy state, the system retains a form of intrinsic vitality. In vacuum physics, the uncertainty relationship between energy and time leads to vacuum fluctuations. On extremely short timescales, virtual particle pairs can continuously emerge and annihilate. These quantum fluctuations produce tangible observational effects. For instance, in the Casimir effect, a weak attractive force arises between two parallel metal plates. In modern technology, the uncertainty principle remains indispensable. The operation of scanning tunneling microscopes relies on the quantum tunneling effect of electrons, enabling atomic-level resolution in observing material surfaces. This technology has become a vital tool in nanoscience research. In precision measurement, the uncertainty principle sets fundamental limits on measurement accuracy. In cutting-edge experiments like gravitational wave detection, scientists must carefully consider the inherent constraints imposed by this principle. From a philosophical perspective, the uncertainty principle profoundly transformed our understanding of causality and determinism. It revealed that, at the microscopic level, nature is fundamentally probabilistic, rather than entirely deterministic. This principle also reminds us that, in the quantum realm, an inseparable connection exists between the observer and the observed system. We cannot act as completely detached bystanders. As in classical physics, the impact of Heisenberg's uncertainty principle has extended far beyond the realm of physics. It has not only transformed our understanding of the nature of reality, but also laid the theoretical foundation for modern technological advancements. From semiconductors to laser technology, from nuclear energy utilization to medical imaging, many achievements of modern civilization are built upon this profound principle. In the familiar world of our daily lives, The state of an object is always clear and definite. A book is either on the table or not on the table. A light is either on or off. This either-or certainty forms the fundamental framework of classical physics. Yet, in the quantum world, the situation undergoes a fundamental transformation. Quantum systems can exist in a superposition of multiple states simultaneously. This superposition is not merely an unknown state, but the system genuinely possessing multiple possibilities at once. Imagine a spinning coin. In the classical world, though we cannot see its heads or tails, it has already landed with one side facing up. In the quantum world, before landing, the coin genuinely exists in a superposition of both heads and tails simultaneously. The existence of this superposition state stems from the wave function description of quantum systems. The wave function simultaneously contains information about multiple possible states, each state possessing a corresponding probability amplitude. The interference effects of these probability amplitudes give rise to the unique phenomena of the quantum world. In classical physics, a system state is described by definite physical quantities. Values for position, velocity, energy, etc. are explicitly defined. In quantum physics, a system state is described by a wave function, containing a weighted combination of all possible states. Measurement also plays fundamentally different roles in the two theories. In classical physics, measurement merely reveals an already existing definite state. In quantum physics, measurement forces the system to collapse from its superposition state into a specific eigenstate. A key feature of quantum superposition is its ability to allow a system to simultaneously explore all possible paths. This is most strikingly demonstrated in the double-slit experiment, where a single particle can pass through both slits simultaneously and interfere with itself. In contrast, classical objects move only along definite trajectories, much like billiard balls rolling across a table, with precisely defined positions and velocities at every moment. Another crucial property of quantum superposition is its capacity to generate quantum entanglement. When two quantum systems interact, their states become intertwined, forming a quantum correlation that transcends classical associations. This fundamental distinction is not merely theoretical, but has been repeatedly verified experimentally, from photon polarization to electron spin, from atomic energy levels to molecular vibrations. Quantum superposition effects are ubiquitous. Understanding the difference between superposition states and classical states is a crucial step into the quantum world. It requires us to abandon classical deterministic thinking and embrace an entirely new probabilistic description. In 1935, physicist Schrödinger proposed a famous thought experiment designed to reveal the seemingly absurd conclusions quantum mechanics might yield at the macroscopic scale. This became the world-renowned Schrödinger's cat. The experiment setup is both ingenious and cruel. Inside a sealed box lies a live cat, a radioactive atom, a radiation detector, and a vial of lethal poison. The entire apparatus is designed such that, if the radioactive atom decays, the detector triggers a mechanism to break the poison vial, resulting in the cat's death. According to the rules of quantum mechanics, the radioactive atom exists in a superposition of decayed and undecayed states. Before opening the box to observe, the entire system remains in a quantum superposition state. This implies the cat exists in an equally bizarre superposition of life and death, neither truly alive nor truly dead, but a peculiar blend of both states. Schrödinger's original intent in proposing this thought experiment was not to debate the cat's fate, but to expose the dilemmas inherent in the Copenhagen interpretation of quantum mechanics. When quantum effects are amplified to macroscopic scales, they yield conclusions that starkly contradict common sense. This thought experiment touches upon a core problem in quantum mechanics: the measurement problem. What process actually causes the wave function to collapse? Where exactly lies the boundary between quantum and classical reality? Different interpretations of quantum mechanics offer varying solutions to Schrödinger's cat. The Copenhagen interpretation posits that the act of observation causes the wave function to collapse only upon opening the box. Is the cat state of life or death determined? The many worlds interpretation proposes that upon opening the box, the universe splits into two branches. In one world, the cat lives. In another, the cat dies. Each world is genuinely real. Decoherence theory offers another explanation. Macroscopic objects cannot maintain quantum superposition because they undergo uncontrollable interactions with their environment. The cat never actually exists in a superposition of life and death because it continuously exchanges information with its environment. From a pragmatic perspective, Schrödinger's cat reminds us that while the mathematical form of quantum mechanics is extremely precise, its physical interpretation remains deeply controversial. This thought experiment acts like a mirror, reflecting the limitations of our understanding of quantum theory. The influence of this thought experiment extends far beyond the physics community. It has become part of popular culture, symbolizing the profoundly perplexing yet captivating questions within science. It reminds us that when exploring nature's deepest mysteries, common sense often becomes the greatest obstacle. Schrödinger's cat has also sparked discussions about the role of consciousness. Some scholars propose that it may be the intervention of consciousness that ultimately causes the wave function to collapse. Though this perspective remains highly controversial, it does point to fundamental unresolved issues within quantum mechanics. In modern quantum technology, we have actually achieved the preparation of microscale Schrödinger's cat states, such as placing a microscopic particle in two positions simultaneously, or maintaining a superconducting circuit in two states at once. These experiments help us better comprehend the transition between quantum and classical realms. Schrödinger's cat thought experiment continues to inspire both physicists and philosophers to this day. Like an ever-burning beacon, it illuminates the most profound and elusive questions in the foundational research of quantum mechanics. When we contemplate this cat that is both alive and dead, we are actually probing a more fundamental question. What is reality? Quantum mechanics tells us that reality may be far more complex and wondrous than we ever imagined. In traditional computers, the basic unit of information is the bit. It functions like a small switch that can only be in an on or off state. We represent these states with 0 and 1. Quantum computers employ entirely different information units, called qubits. Their key distinction from classical bits lies in their ability to exist simultaneously in a superposition of 0 and 1. Imagine a spinning coin. Before it comes to rest, you cannot determine whether it will land heads or tails. A qubit resembles this spinning coin, embodying the possibility of both states simultaneously. This superposition state grants quantum computers unique capabilities. When a quantum bit is in superposition, it simultaneously processes both possibilities. 2 quantum bits can represent 4 states at once. As the number of quantum bits increases, this parallel processing power grows exponentially. Problems that require step-by-step computation on traditional computers can be tackled by quantum computers exploring all possible solutions simultaneously. It's like navigating a maze. A traditional computer must try each path individually, while a quantum computer can explore all paths at once. Another remarkable property of qubits is entanglement. When multiple qubits become entangled, a special connection forms between them, changing the state of one entangled qubit instantly affects the other entangled qubits. This entanglement enables quantum computers to tackle extraordinarily complex problems, such as rapid searches within vast datasets, or simulating intricate molecular structures. Scientists are currently exploring multiple technologies to realize qubits, including superconducting circuits, ion traps, and photonic systems. Each approach has distinct advantages and limitations. Quantum computers are not intended to replace conventional computers. Each excels in different domains. Quantum computers excel at solving specific problem types, such as cryptography, drug design, weather forecasting, and other complex computations. Building practical quantum computers still faces many challenges. Quantum states are extremely fragile and susceptible to external interference, requiring ultra-low temperatures and sophisticated isolation equipment. Nevertheless, quantum computing has demonstrated immense potential, ushering in a new era of computational science, enabling solutions to problems beyond the reach of conventional computers. In the microscopic quantum realm, particles can maintain remarkable superposition states. Yet, in our familiar macroscopic world, objects always exist in definite states. The key to this difference lies in the phenomenon of decoherence. Decoherence can be understood as the leakage caused by a quantum system interacting with its environment. When a quantum system comes into contact with its surroundings, its quantum properties gradually dissipate. Imagine tossing a pebble into a calm lake. Clear ripples form. If a strong wind blows across the lake, the ripples quickly vanish. Environmental influences act like this gust of wind, disrupting the delicate structure of quantum systems. Schrödinger's cat cannot exist in a superposition of life and death in reality, because the cat is a complex system composed of trillions of atoms. These atoms constantly exchange energy and information with their surroundings. Collisions of air molecules within the box, minor fluctuations in ambient temperature, even radiation from distant galaxies. Constantly observe this system. These minute interactions accumulate, rapidly destroying the quantum superposition, causing the cat to settle into a definite state of either life or death within an instant. The decoherence process occurs so swiftly that we cannot detect quantum superposition in macroscopic objects. Understanding decoherence not only clarifies the boundary between classical and quantum realms, but also charts the course for quantum technology development. Scientists are actively seeking better methods to extend the coherence time of quantum states. Now relax your mind. There's no need to worry about encountering a cat that is both alive and dead. In our warm and tangible world, quantum oddities exist solely in the microscopic realm. You can rest assured as you drift into sleep. Imagine a pair of twin particles that grew up together. They developed a special kind of understanding. After these two particles were separated, no matter how far apart they were, their states remained mysteriously linked. This connection is quantum entanglement, one of the most wondrous phenomena in the quantum world. When two particles become entangled, they form an inseparable whole. Let's understand this with a simple analogy. Imagine a special pair of gloves, a left glove and a right glove. When you place each glove into separate boxes and randomly send them to opposite ends of the earth, before opening the boxes, you have no idea which glove is in which box. But the moment you open one box, and see the left glove, you instantly know the other box must contain the right glove. Yet quantum entanglement is even more astonishing than this example. In the quantum realm, the gloves are not fixed before the boxes are opened. They exist in a superposition state, simultaneously both the left glove and the right glove. Only when one box is opened do both gloves instantly determine their identities. The most astonishing aspect of this phenomenon is that this connection is established instantaneously, unrestricted by distance, even if two particles are located at opposite ends of the universe. This tacit understanding between them persists. Scientists have experimentally confirmed this connection by separating entangled particle pairs hundreds of kilometers apart and measuring the state of one particle, only for the other particle to instantly respond accordingly. This connection appears to exceed the speed of light, yet it does not violate physical laws, because no information is transmitted. The non-locality exhibited by quantum entanglement suggests the universe may be more interconnected than we imagine. In some profound sense, separation might be merely an illusion. When the concept of quantum entanglement was first proposed, Einstein expressed strong skepticism. He termed this phenomenon spooky action at a distance, arguing it violated fundamental principles of physics. Together with two colleagues, Einstein proposed a famous thought experiment to prove the incompleteness of quantum mechanics. They posited that some hidden variables must exist to determine the future states of particles. This debate persisted for decades, until physicist John Bell devised an ingenious scheme to experimentally test who was correct. Bell formulated a mathematical inequality. If Einstein's hidden variable theory held true, experimental results should satisfy this inequality. If quantum mechanics prevailed, results would violate this inequality. With advances in experimental technology, scientists began conducting this crucial test, a series of increasingly precise experiments ultimately yielded identical outcomes. The experimental results unequivocally violated Bell's inequality, supporting quantum mechanics predictions. This meant Einstein's hoped-for hidden variable theory did not align with experimental observations. This result sent shockwaves through the physics community and revealed that quantum entanglement is genuinely real, not some undiscovered hidden variable at work. These experiments also demonstrated that quantum correlations truly transcend any classical correlations and exhibit genuine quantum properties. Although Einstein was mistaken in his judgment on this issue, his skepticism propelled the entire field forward, compelling scientists to delve deeper into the meaning of quantum mechanics. Despite quantum entanglement demonstrating instantaneous correlations, we still cannot use it to achieve superluminal communication. This is a subtle arrangement of nature. The key lies in the randomness of measurement outcomes. When we measure an entangled particle, the result is entirely random. We cannot control what state it will manifest. Suppose we attempt to transmit information using entangled particles, such as sending a yes or no signal. We might agree that if the particle appears in state A, it represents yes, and state B represents no. The problem is, we cannot control which state the particle will appear in. Each measurement is like flipping a coin. The outcome is entirely random. The receiver can instantly know what we measured, but they cannot determine if this result was deliberately chosen by the sender, or if it appeared randomly. This is like two people each holding an entangled particle, located on two separate planets. When one person measures their particle, they obtain a random result. The other person immediately receives the corresponding result. But both results are random. Since neither party can control the measurement outcome, They cannot transmit any meaningful information through this method. The existence of this randomness safeguards the law of causality from being violated, ensuring information transmission never exceeds the speed of light. This exquisite design in nature permits the existence of miraculous quantum correlations, while upholding the physical laws we know. Though unusable for faster-than-light communication, quantum entanglement holds vital applications in modern technology, most notably in quantum cryptography. Leveraging entanglement's properties enables creation of absolutely secure communication channels. Any eavesdropping attempt disrupts the entangled state, immediately detected by both parties. In quantum computing, entanglement is key to achieving quantum parallelism, enabling quantum computers to process vast amounts of information simultaneously, solving problems beyond the reach of traditional computers. Quantum entanglement also plays a role in precision measurement. By leveraging entangled particles' sensitivity to minute changes to create extremely precise sensors. Beyond technological applications, quantum entanglement offers profound philosophical insights, suggesting the universe may be an indivisible whole. At a profound level, an intrinsic connection may exist between all things. Separation and isolation may merely be superficial phenomena. This concept resonates with certain ancient philosophical ideas. The Eastern philosophy of unity of heaven and humanity finds scientific resonance in quantum entanglement. Quantum entanglement reveals that nothing in the universe exists in isolation. Deep interconnections bind all things together. This connection exists not only between microscopic particles, but may also manifest in some form within the macroscopic world. When we gaze at the stars and contemplate the cosmos, quantum entanglement reminds us that an invisible bond may exist between us and distant celestial bodies. In our everyday experience, if confronted by a high wall, cannot be scaled without sufficient energy, just as a small ball rolling over a hill requires adequate initial velocity, or it will roll back halfway. Yet, in the quantum realm, a remarkable transformation occurs. Microscopic particles can sometimes traverse energy barriers deemed insurmountable by classical physics. This phenomenon is known as quantum tunneling. Imagine an electron encountering an energy barrier. According to classical physics, if the electron's energy is lower than the height of the barrier, it should be reflected back with 100% probability, just as a tennis ball bounces off a wall. Yet, experimental observations reveal the electron does indeed have a certain probability of appearing on the other side of the barrier, as if it found an invisible tunnel through the wall. This is the origin of the name quantum tunneling. This phenomenon exists not only in theory, it can be directly observed and measured in laboratories, and its occurrence probability can be precisely calculated, perfectly matching the predictions of quantum mechanics. The probability of quantum tunneling depends on several key factors: the height and width of the barrier, the mass of the particle, and the energy of the particle. The lower and narrower the barrier, and the smaller the particle's mass, the greater the probability of tunneling. What makes this effect astonishing is its complete defiance of our classical intuition. In the macroscopic world, we would never witness a soccer ball spontaneously passing through a gymnasium wall. Yet, in the microscopic realm, this is a commonplace phenomenon. To understand the mechanism of quantum tunneling, we must revisit the concept of the wave function. In quantum mechanics, particles are described by wave functions. The square of the absolute value of the wave function gives the probability of finding the particle at any point in space. When a quantum particle encounters a potential barrier, Its wave function does not abruptly cut off at the barrier's edge. Instead, it penetrates into the barrier with exponential decay, like a tail that gradually tapers off, and extends to the other side of the barrier. This exponentially decaying wave function rapidly diminishes within the barrier, but never completely vanishes to zero. If the barrier isn't too wide, the tail of the wave function can extend beyond the barrier's edge. This means the particle has a non-zero probability of appearing on the other side of the barrier. We can grasp this with a vivid analogy. Imagine a drop of ink spreading on blotting paper. Though most of the ink is absorbed, a minuscule amount still permeates to the other side. Quantum tunneling resembles this probabilistic permeation. This description not only explains the tunneling phenomenon, but also precisely predicts the tunneling probability. By solving the Schrödinger equation, we can calculate the decay rate of the wave function within the barrier, and thereby determine the probability of particle tunneling. Crucially, this interpretation has been confirmed by countless experiments. From atomic physics to condensed matter physics, predictions of quantum tunneling show remarkable agreement with experimental measurements. The quantum tunneling effect is far from a laboratory oddity, plays an indispensable role in both nature and modern technology. Consider first the mechanism of stellar luminosity. In the cores of the Sun and other stars, hydrogen nuclei must undergo nuclear fusion to form helium. This process releases immense energy. However, atomic nuclei carry positive charge and experience strong electrostatic repulsion between each other. According to classical physics calculations, even at the high temperatures within stellar cores, the average kinetic energy of atomic nuclei is far insufficient to overcome this electrostatic barrier. The quantum tunneling effect provides the solution. Due to the existence of quantum tunneling, hydrogen nuclei possess a certain probability of traversing this electrostatic barrier, enabling nuclear fusion to occur. It is precisely this effect that enables the Sun to continuously emit light and heat, providing the energy source for life on Earth. Without quantum tunneling, no stars would shine in the universe, and life could never have emerged. This quantum effect at the microscopic level actually determines the appearance of the macroscopic universe. In modern technology, quantum tunneling is equally indispensable. Its most famous application is the scanning tunneling microscope. The core principle of this microscope is based on the quantum tunneling effect. When an extremely sharp metal probe approaches the surface of a sample without making actual contact, electrons flow between the probe and sample due to quantum tunneling, forming a tunneling current. The magnitude of this tunneling current is extremely sensitive to the distance between the probe and sample. A distance change of just 1 atomic diameter can cause the current to fluctuate by a factor of 10. Leveraging this sensitivity, the scanning tunneling microscope can see surfaces with atomic-level resolution. It not only observes individual atoms, but also manipulates and moves them, opening the door to nanotechnology. Beyond these classic applications, quantum tunneling plays a role in numerous other fields. In semiconductor devices, it determines the characteristics of certain electronic components. In chemical reactions, it influences the rates of certain reactions. And even in biology, it may be involved in certain enzyme-catalyzed reactions. The quantum tunneling effect reveals to us that quantum mechanics is not merely an abstract theory, but tangibly shapes the world around us. From the birth of stars to technological progress, this seemingly mysterious quantum phenomenon plays a ubiquitous and crucial role. In our previous understanding, The universe was constructed from minute fundamental particles. Much like Lego bricks forming various structures, particles such as electrons and quarks were considered indivisible building blocks, a perspective termed particle ontology. However, modern physics has brought about a major paradigm shift. Quantum field theory proposes an entirely new ontology. Within this theoretical framework, the most fundamental entities in the universe are not particles, but various fields permeating all of space. Imagine an endless ocean. This ocean is the fundamental background of the universe. Within this ocean, different types of waves exist. The electromagnetic field is like a surface capable of producing ripples. The electron field is another body of water with specific properties. When we say we observe an electron, we are actually observing a specific location within the electron field, observing a particular excitation. This excitation manifests in space as a localized particle, but is fundamentally a vibration of the field. The photon is similarly an excitation of the electromagnetic field. When the electromagnetic field vibrates in a specific manner, we say we have observed a photon. This conceptual shift has fundamentally altered our understanding of the nature of matter. Particles are no longer independent, tiny entities, but rather manifestations of the quantum fields behind them. Every fundamental particle has its corresponding field. These fields permeate the entire universe. Even in the seemingly empty vacuum, these fields persist, merely existing in their lowest energy state. When we say space is empty, we are actually stating that all fields are in their ground state. But this does not imply these fields cease to exist. They still fill the entire space, ready to be excited and generate particles. According to the uncertainty principle of quantum mechanics, even in the lowest energy state, a physical system cannot remain completely at rest. Subtle fluctuations always exist. In quantum field theory, these fluctuations manifest as the continuous creation and annihilation of virtual particles. Unlike real particles, virtual particles cannot be directly detected. They have extremely short lifespans and violate the classical mass-energy relationship. Imagine the vacuum as a boiling ocean, where particle-antiparticle pairs constantly spawn out of thin air, only to annihilate each other in an instant, returning to the sea of energy. This process does not violate the law of energy conservation, because according to the time-energy uncertainty principle, at extremely short timescales, the uncertainty of energy permits such fluctuations. Though these virtual particles cannot be directly observed, their effects are genuinely measurable. For instance, in hydrogen atoms, electron interactions with these vacuum fluctuations cause minute shifts in its energy levels. This is the famous Lamb shift. Another significant effect is virtual particles slightly altering the electron's magnetic moment. Theoretical predictions and experimental measurements align with exceptional precision, making this one of quantum electrodynamics' most successful predictions. The concept of virtual particles also aids our understanding of the nature of forces. In quantum field theory, interactions between particles are mediated by the exchange of virtual particles. For instance, the electromagnetic force is transmitted through the exchange of virtual photons. In 1948, Dutch physicist Casimir proposed an ingenious thought experiment that could directly verify the existence of vacuum fluctuations. Imagine placing two parallel metal plates in a vacuum. When the plates are brought extremely close together, typically separated by only a few micrometers, a weak attractive force arises between them. This effect can be explained by vacuum fluctuations. Outside the metal plates, virtual photons of all wavelengths can exist. However, within the narrow space between the plates, only those virtual photon modes whose half wavelengths are integer multiples exactly matching the plate spacing can exist. This results in more virtual photon modes outside the plates than between them. The resulting pressure difference causes the plates to approach each other. Measuring the Casimir effect is extremely challenging. Due to its demanding experimental conditions, it requires an extremely high vacuum, precise distance control, and highly sensitive force measurement devices. It was not until 1997 that scientists first measured the Casimir force, with an accuracy exceeding 5%. Subsequent experimental techniques have continuously advanced, enabling precise verification of this effect across various geometric configurations. The Casimir effect not only confirms the reality of vacuum fluctuations, but has also found practical applications in nanotechnology. In microelectromechanical systems, MEMS, the Casimir force may cause component adhesion. This has become a critical factor in design considerations. Simultaneously, scientists are exploring how to harness the Casimir effect for contactless actuation of microscopic devices. Within the theoretical framework of the Standard Model exists a unique field, the Higgs field. Unlike other fields, the Higgs field possesses a non-zero vacuum expectation value, meaning it permeates all of space, even in its unexcited state. We can envision the Higgs field as an invisible syrup, permeating every corner of the universe. When other particles move through this syrup, they encounter resistance, manifesting as particle mass. Different particles couple to the Higgs field with varying strengths, explaining why fundamental particles possess distinct masses. Photons and gluons do not couple to the Higgs field, and thus have no mass. W and Z bosons, however, strongly interact with the Higgs field, and thus possess significant mass. In 2012, scientists at the Large Hadron Collider announced the discovery of the Higgs boson, the excited state of the Higgs field. This discovery completed the final piece of the Standard Model puzzle. The confirmation of the Higgs mechanism not only explains the origin of particle mass, but also reveals the profound concept of symmetry breaking. In the high-temperature state of the early universe, the Higgs field had an expectation value of 0. All particles were massless. As the universe cooled, the Higgs field acquired a non-zero expectation value, and particles consequently gained mass. This discovery deepens our understanding that the vacuum is not empty, but filled with various fields. The structure and properties of these fields determine the behavioral characteristics of elementary particles and shape the universe as we know it. In our journey to explore the most fundamental constituents of matter, physicists have constructed an elegant theoretical framework known as the Standard Model of particle physics. It serves as a recipe for the universe, revealing the basic ingredients composing reality. First, let us recognize the fundamental building blocks of matter. They are divided into two main families, quarks and leptons. Each generation possesses its own unique properties. The first generation includes the up quark and the down quark. They form the primary matter of our everyday world. The proton consists of 2 up quarks and 1 down quark. The neutron comprises 2 down quarks and 1 up quark. These lightest quarks combine to form the core of atomic nuclei. Accompanying the quarks is the lepton family. The most famous member is the electron, orbiting outside the atomic nucleus. It determines an element's chemical properties. The electron's neutral counterpart is the electron neutrino. This ghostly particle barely interacts with matter. Second and third generation particles seem like heavier versions of first generation particles. They carry the same electric charge, but possess greater mass, and are rarer in the universe. The second generation includes the charm and strange quarks, along with the muon and muon neutrino. The third generation comprises the top and bottom quarks, and the tau and tau neutrino. Why these particles are divided into 3 generations remains a mystery in physics, but we know only first-generation particles compose the stable matter around us. Beyond these matter particles, the Standard Model features another crucial class, bosons. They are force carriers, responsible for interactions between particles. Within the Standard Model framework, fundamental forces in nature are transmitted through boson exchange. These force-carrying particles, like messengers, convey interactions between matter particles. First is the most familiar electromagnetic force. This carrier is the photon, the particle of light. Electromagnetic force governs interactions between atoms and molecules, determining all chemical phenomena. From the flames of combustion to the processes of life, the electromagnetic force is indispensable. The unique characteristics of the photon are its lack of mass and its propagation at the speed of light. This grants the electromagnetic force an infinite range of action. Next is the weak force, transmitted by 3 heavy bosons, the W+, W-, and Z bosons. Though the weak force has an extremely short range, plays a pivotal role in cosmic evolution. Its most famous effect is initiating radioactive decay in certain atomic nuclei by transforming a neutron into a proton, or vice versa. This transformation underpins stellar energy production and serves as a vital mechanism for element synthesis. The strongest force is the strong force, carried by 8 gluons, binding quarks within protons and neutrons. The strong force exhibits a unique property. Its strength increases with distance. This ensures quarks can never be observed individually. The strong force acts not only between quarks, but also binds protons and neutrons within atomic nuclei through residual interactions. This nuclear force overcomes the electromagnetic repulsion between protons, enabling stable atomic nuclei. The Standard Model stands as a magnificent achievement of human intellect. It has withstood countless experimental tests, with astonishing predictive accuracy. Some predictions match experimental results, with a precision equivalent to measuring the distance from Earth to the Moon, with an error no greater than the width of a human hair. Yet this model is far from perfect. It still faces several major unsolved mysteries. The most glaring omission is gravity. Among the 4 fundamental forces we know, only gravity has yet to be successfully quantized. Einstein's general theory of relativity elegantly describes gravity's macroscopic behavior, but remains difficult to reconcile with the quantum framework of the Standard Model. Another enigma is dark matter. Astronomical observations indicate the visible matter in the universe is insufficient to explain the rotational speeds of galaxies and the dynamics of galaxy clusters. A form of matter must exist that does not emit light, yet exerts gravitational effects. Yet among all particles in the Standard Model, none can account for dark matter's properties. This implies that the vast majority of cosmic matter is composed of particles we have yet to discover. Most perplexing is dark energy. Observations reveal the universe is not only expanding, but accelerating its expansion. This accelerated expansion requires a repulsive energy, dark energy, to drive it. Dark energy constitutes nearly 70% of the universe's total energy. Yet we know almost nothing about its nature. It lies beyond the scope of the Standard Model's descriptions. It may well be the greatest mystery in physics this century. Despite these unresolved enigmas, the Standard Model remains humanity's most powerful theoretical framework. For understanding the microscopic world, it reveals that the fundamental structure of the universe is more intricate and more mysterious than we ever imagined. In the journey of exploring the microscopic world, one theory has earned widespread acclaim among physicists for its astonishing precision. This is quantum electrodynamics. Quantum electrodynamics is the quantum theory, describing the interaction between light and charged particles. It reveals how electrons and photons communicate, how they exchange energy, and how they dance together in the microscopic realm. The development of this theory spanned decades of exploration, from Dirac's relativistic electron equation to the complete formulations by Schwinger, Feynman, and Shinichiro Tominaga. QED finally took shape in the mid-20th century. Imagine this scene: an electron moving through space. It continuously emits and absorbs virtual photons. These fleeting virtual photons act like shadows of the electron, accompanying every step of its journey. When two electrons approach each other, they exchange virtual photons to transmit electromagnetic forces. This process resembles two ice skaters tossing a ball back and forth. Each exchange alters their respective states of motion. QED not only describes this force transmission, but also explains every detail of light-matter interactions, from the frequencies of atomic light emission to the behavior of electrons in magnetic fields. All fall within its domain. The beauty of this theory lies in its seamless integration of quantum mechanics and relativity, providing a self-consistent physical picture that enables us to understand the interaction between high-speed charged particles and electromagnetic fields, to grasp how quantum electrodynamics performs calculations. We must recognize the powerful tool of Feynman diagrams. These seemingly simple diagrams actually form a sophisticated visual language. Each Feynman diagram tells a story, describing how particles meet, interact, and part ways. Straight lines represent electrons. Wavy lines represent photons. Their intersection points mark where interactions occur. Yet these diagrams are more than mere schematics. Each corresponds to precise mathematical expressions. The direction of lines, the manner of their meeting, all follow strict rules. Feynman's genius lay in developing a systematic method to rank and calculate all possible interaction diagrams by their significance. Yet a deeper concept is path integration. This idea reveals that when a particle travels from point A to B, it doesn't follow just one path. Instead, it simultaneously explores all possible routes. Consider a person traveling from home to school. They don't merely take the shortest route. Simultaneously, in a certain sense, they traverse every possible detour. The final outcome is the superposition of all paths. In the quantum world, each path carries a phase. These phases interfere with one another. Some reinforce, others cancel, ultimately determining the particle's behavior. This mindset of considering all possibilities stands as one of quantum theory's most fundamental insights. It enables us to calculate the probability of seemingly impossible quantum processes occurring. The precision of quantum electrodynamics stands as a miracle in scientific history. The agreement between its predictions and experimental measurements reaches an astonishing level. Take the electron's magnetic moment, for example. This physical quantity describing an electron's behavior in a magnetic field has been studied with extremely high precision through both theory and experiment. Quantum electrodynamics not only calculates the electron's magnetic moment, but also precisely predicts its minute deviation from the classical value. This quantity, known as the anomalous magnetic moment, has become a crucial touchstone for testing the theory. Experimental physicists, through ingenious designs, measure the numerical value of the electron's magnetic moment. Theoretical physicists perform complex calculations. The results from both sides remain identical to 11 decimal places. This precision is equivalent to measuring the distance between Earth and the Moon, with an error no greater than the thickness of a human hair. In the history of science, few theories have achieved such extraordinary accuracy. Another famous example is the Lamb shift. The energy levels of hydrogen atoms do not align perfectly as predicted by Dirac theory, but exhibit a subtle shift. This shift arises precisely from the interaction between electrons and vacuum fluctuations. Quantum electrodynamics not only predicted the existence of the Lamb shift, but also precisely calculated its magnitude, which perfectly matches experimental measurements. These successful predictions have made quantum electrodynamics one of the most rigorously tested theories in physics, demonstrating the precision and elegance achievable when mathematics engages in profound dialogue with nature. Among the marvels of the quantum realm, the delayed choice experiment stands as one of the most thought-provoking. This thought experiment, originally proposed by physicist John Wheeler, has now been realized in the laboratory. Imagine an enhanced double-slit apparatus. A photon first passes through a beam splitter, then can choose between two possible paths. Finally, at the endpoint, we may choose whether to measure the photon's path information. The crucial point is this choice is made after the photon has passed through the beam splitter, meaning after the photon decides how to behave. We then decide what question to ask it. Experimental results show, if we choose to measure the path information at the end, the photon behaves like a particle, forming two distinct bright spots. If we choose not to measure the path information, the photon behaves like a wave, forming interference fringes. This seems to imply that our present choice can influence the photon's past behavior. The future measurement method determines the photon's past identity. This phenomenon can be likened to a maze. You wander randomly through the maze until reaching the exit, when you're told whether to seek the shortest path or the most interesting route, and your recorded path will magically align with the final requirement. On a cosmic scale, Wheeler envisioned an even grander version, observing distant quasars through gravitational lensing, after photons traverse billions of years of the universe. Ultimately, we determine whether it arrived along a single path or simultaneously along multiple paths. This experiment forces us to rethink the nature of time. At the quantum level, the boundary between past and future seems far less distinct than we imagined. If the delayed choice experiment is perplexing, the quantum erasure experiment is even more wondrous. It reveals the magic of information and the resilience of the quantum world. In the standard double-slit experiment, once we obtain information about the particle's path, the interference fringes vanish. The core idea of the quantum erasure experiment is, if we could erase this path information, would the interference fringes reappear? The experimental setup is meticulously designed, with specific optical elements added after the double slit. These elements mark the photon's path, while simultaneously preserving the possibility of erasing this marking. When the experiment begins, if we read the path information, the screen displays two bright spots, with no sign of interference. But the magic happens. When we choose to erase the path information, the interference fringes reappear, as if we had never made the measurement at all. This is akin to an artist first painting on a canvas, then covering it with special pigment. When viewers choose to wear specially designed glasses, the covering layer becomes transparent, and the original painting reappears. The quantum erasure experiment reveals that in the quantum world, information itself possesses physical effects. Knowing what information is accessible is equally important to actually acquiring that information. This experiment not only deepens our understanding of quantum measurement, but also provides crucial insights for quantum computing and quantum communication. The delayed choice and quantum erasure experiments reveal that the space-time perspective of the quantum world drastically diverges from our everyday experience. In classical physics, time flows unidirectionally. Causality strictly follows temporal order. Causes must precede. Effects must follow. Yet, in the quantum realm, this strict causality appears to blur. Future choices can influence past actions, and information erasure can alter the manifestation of events already occurred. This does not violate relativity, since no superluminal information transfer occurs, but it does challenge our deep-seated intuition about the nature of time. Some physicists suggest these experiments hint that past and future may coexist. Like a completed tapestry, we are merely unfolding it step by step. Other interpretations propose time itself might be an emergent phenomenon, arising from deeper quantum processes. Whatever the ultimate explanation, these experiments reveal the universe operates far more intricately than we imagined. In this wondrous quantum realm, the direction of causality's arrow may prove more flexible than we assume. The passage of time may be more complex than we perceive. In the classical physics worldview, the universe resembles a precision clock, where knowing initial conditions and all laws allows predicting every future detail. This perspective is called determinism. Yet quantum mechanics revolutionized this understanding. In the microscopic realm, randomness isn't due to our ignorance, but nature's intrinsic essence.
Imagine to si na coin.
From a classical physics perspective, if we knew the initial velocity, air resistance, and every detail, we could precisely predict whether it would land heads or tails. This is merely superficial randomness. But in the quantum world, the situation is entirely different. When we measure a particle in a superposition state, the outcome is fundamentally unpredictable. It's as if the universe is truly rolling the dice. This intrinsic randomness is vividly demonstrated in the single-photon double-slit experiment. We can never predict exactly where a single photon will land on the screen, only its probability distribution. Radioactive decay offers another example. We cannot predict when a specific atomic nucleus will decay, only its probability of decay within a given time interval. Einstein expressed strong dissatisfaction with this, uttering his famous line, "God does not play dice." Yet extensive experimental evidence indicates that this randomness is indeed a fundamental characteristic of nature. Quantum randomness differs from any classical random process. It arises not from hidden variables or our ignorance, but from an inherent property of the laws of nature themselves. ####14.2 Einstein's objections and the philosophical debate. The debate between Einstein and Bohr regarding quantum randomness stands as one of the most famous controversies in scientific history. This dispute persisted for decades and profoundly influenced the development of physics. Einstein could never accept the notion that the universe is fundamentally random. He believed that God does not play dice, and that deeper underlying laws must exist that we have yet to discover. In his view, the probabilistic descriptions of quantum mechanics were incomplete, and some hidden variables must exist to determine seemingly random quantum processes. Bohr held a different perspective, arguing that quantum mechanics was already a complete theory, and we must accept the inherently probabilistic nature of reality. This debate transcended mere scientific disagreement, delving into profound philosophical questions about the nature of reality, the limits of knowledge, the meaning of causality. It was only when Bell proposed his inequality that this debate could be resolved experimentally. The experimental results unequivocally supported Bohr's position, proving that any local hidden variable theory was incompatible with experimental observations. Yet Einstein's skepticism propelled the development of foundational research in quantum mechanics. His critiques served as a whetstone, sharpening and deepening quantum theory. ####14.3 Order within randomness and structured probability. Though individual quantum processes appear random, the statistical behavior of numerous quantum events reveals remarkable regularity. Consider rolling a die. A single roll yields randomness. Yet, after thousands of rolls, the frequency of each face approaches equilibrium. In the quantum realm, this statistical regularity proves even more precise and profound. The probability predictions provided by wave functions are consistently validated through repeated large-scale experiments. The half-life of radioactive elements embodies this regularity. While we cannot predict when a single atom will decay, the decay behavior of a large number of atoms strictly follows an exponential decay pattern. Probability in quantum mechanics is not unstructured randomness, but highly organized probability. It follows rigorous mathematical laws, evolving through the Schrödinger equation. This structured randomness endows the quantum realm with both profound uncertainty and deep-seated order. It strikes a delicate balance between innovation and stability. In a sense, quantum randomness provides the universe with a wellspring of creativity and diversity. It allows novel phenomena to emerge and makes evolution possible. Our quantum journey is nearing its end. From Planck's reluctant energy quantization to Einstein's bold photon hypothesis, from the profound enigma of the double-slit experiment to the elegant mathematics of the Schrödinger equation, we have wandered together through the strange landscapes of the quantum realm. Thank you for investing this time to explore this subtle realm with me. Your listening and contemplation have stirred these abstract concepts into tangible ripples across the ocean of consciousness. Now gently withdraw your attention from the quantum mist back to present reality. Feel the support beneath your mattress. Listen to the subtle sounds within the room. Notice the gentle rhythm of your breath. The peculiar rules of the quantum world still operate within every atom of your body. But in this moment, you need not understand them. Simply feel existence itself. At the end of this exploration, we may discover the deepest comfort comes from knowing we are not bystanders in the universe, but the very way it contemplates itself. Quantum mechanics tells us certainty may be a luxury, yet within uncertainty lies freedom. We need not be all-knowing or all-powerful to exist peacefully within this universe. The air you breathe, the warmth of your body, your consciousness in this moment, are all ways the universe expresses itself. In this vast and wondrous cosmos, your very existence is the most beautiful miracle. No need for complete understanding. No need for total mastery. Only the acceptance of this truth. You belong here and now. Now let your awareness slowly fade. Let the wonders of the quantum world become the fabric of your dreams. Perhaps in some parallel universe, another you continues to explore. Perhaps in tonight's dreams, you'll meet the cat that is both alive and dead. May you find profound peace in your sleep and connect with the universe's source in unconsciousness. When you awaken tomorrow, carry fresh wonder for the world and continue this never-ending exploration. Good night, dear explorer. May starlight guard your dreams. May quantum fluctuations bring you sweet slumber. We'll meet in dreams, in the ocean of consciousness, to continue this eternal dialogue. Good night.